Welcome, and thank you for joining us today as part of the Google Cloud Partner Analyst Series. My name is Bonnie Peterson, and I lead the Go-to-Market Partner Marketing team for North America at Google Cloud. Today, we will be hearing from Paul Miller at Forrester and Manju Devadas at Google Premier Partner Pluto7 in their presentation, Putting Manufacturing to Work in Digital Twins. Topics discussed will include IoT's relationship to data and how it is put to use, as well as enabling value engineering and manufacturing. Q&A will follow at the conclusion. Paul, over to you.
Thank you very much, Bonnie, and hello, everybody. As Bonnie said, my name is Paul Miller. I'm a principal analyst at Forrester based in the UK. And most of the time, my research area of coverage is manufacturing, Industry 4.0, smart manufacturing, and related terms. Today, I'm going to be talking to you specifically about the use of digital twins in the manufacturing sector. And as we look at digital twins and as we look at manufacturing, I think consistently we see quite a lot of confusion. There are lots of stakeholders, lots of vendors, lots of potential beneficiaries talking about digital twin. But there's a real danger, I think, that they're talking past one another. They're latching on to a term without completely understanding what it is, and then getting very excited about potential, very excited about opportunity, but not necessarily reaching a common ground where they really talk about the same thing and where they can really understand the problem, the opportunity, the potential, and ways to work together. So what I wanted to do in this session is to share some of Forrester's views on what a digital twin really is, what a digital twin probably isn't, and then look at some of the use cases where digital twin make most sense. And I think that should then lead quite nicely into Manju's presentation about Pluto7 and some of the ways they work with their customers to really solve tangible, recognizable problems using digital twin. So that's the plan. Let's get going with the conversation. And firstly, I think it's important to recognize the relationship between IoT, the Internet of Things, and the digital twin. And as we look at the way that IoT is used in the manufacturing sector, we really do see sort of three main phases in that adoption journey. The first phase is the simplest one, and it's where almost everybody tends to start. It's putting an IoT sensor onto some remote asset simply so you know what that asset is doing. Imagine you are managing a fleet of wind turbines scattered across a Scottish hillside in the Highlands, and your control room is quite a long way away from that. You want to know that those turbines are working right now. You want to know that those turbines are generating power right now. And so you connect them. You turn them into a connected asset. And that connection simply allows you to know that turbine 27 is spinning in the wind right now, and it's generating a certain amount of power. Turbine 14 is not operating right now, and maybe you need to send an engineer out to have a look and work out what's going on. Very, very simple, not making any use of rich predictive analytics, not making any use of rich machine learning and some of the things that Manju will talk about. Simply a connection to a distant asset to know what it's doing. There's value there, but it's not really getting into some of the rich, exciting opportunities. The second phase is where things get a little more interesting, where you start to gather data from these connected assets and you start to build models about the way they behave, both right now, but also in the past. And you use those models and you use that data to start anticipating what might happen in the future. And the prime example of this is predictive maintenance, gathering information about how a particular type of machine normally operates, gathering information about what failure states and problem states and warnings might look like, and using that to predict next best action. Using that to say, back to the wind farm example, wind turbine 27 is running 2 degrees hotter than normal. It's been doing so for the past 48 hours. Based on previous knowledge of other wind turbines like it, that probably means one of the motors is wearing out. It probably means it's going to fail in the next 7 days. And therefore, obviously, let's send an engineer out in the next within the next 7 days so they get there to fix the problem before it becomes more serious. And we see lots of examples of that. Then the third phase, which we won't really talk about today, is where you start to use this data to drive completely new business models, where you shift from selling a physical asset towards delivering a service or an outcome powered by that asset. And for example, Kaeser Compressor, a company in Germany that makes compressed air machines, they shifted from selling those physical compressed air machines towards effectively selling liters of compressed air, powered by IoT, powered by analytics, and powered by a very different relationship with their customers and their suppliers. So those are the three phases broadly that we see as organizations adopt IoT. And digital twin touches the first one a little bit, absolutely touches the second one, and also fundamentally powers the third use case. So really, digital twin is about putting that IoT data, that connected asset data, to use. And within Forrester, we define digital twin very simply. We say that a digital twin is a digital representation of a physical thing's data, state, relationships, and behavior. Quite simple, quite straightforward, and broadly the definition that you would hear from almost anybody in the field. The words change a little bit. Some of the definitions are a lot longer, but broadly, this is the essence that most digital twin definitions try to capture. And using this as a definition, we surveyed Forrester clients to try and understand what their use of digital twins might be. And within the manufacturing sector, looking at our latest survey data in this particular context, in the manufacturing sector, 16% of respondents are currently implementing digital twin in their business. A further 24% plan to do so in the next 12 months. And this data is from 2019, so pre-pandemic. I think looking at some of the use cases we've seen for digital twin in the pandemic, that 24% number has probably gone up quite a bit because we're seeing real, tangible, demonstrable benefit from putting digital twin to use as part of the way in which manufacturing organizations are responding and adapting to the pandemic. All those remote assets, like the wind farms I was talking about earlier, all those remote assets that are now much harder to reach, it becomes much more important to connect them so you can keep an eye on them from afar. You have fewer field service engineers to send out to fix things, so you need to make better use of the engineers you have. You have problems crossing borders, perhaps. You problems putting people on planes. And so all of this requires you to be much more intelligent about how you use that limited expert human resource. And connecting those assets up and building models around them is one way to allow you to task those limited human resources much better. You really send them where they're absolutely required, rather than sending them out on the off chance to just go and inspect something that might be about to fail one day. Much better to send an engineer out to a critical component that's going to fail very soon and have them fix that problem. I said at the start that we see a lot of confusion around what a digital twin is and what it's used for. I've already shared Forrester's definition of a digital twin, but now we've gone a step further than that. And what we're saying very clearly is that to be a digital twin, you really have to demonstrate all 6 of the key characteristics you can see on this slide. If you only demonstrate a few of them, you're not a digital twin. If you don't demonstrate any of them, you're absolutely not a digital twin. And so just to talk about each of these 6 characteristics briefly in turn. And the first one, physical and virtual, should be completely obvious. A digital twin requires a physical twin as well. To be a twin, there have to be 2 of you, one physical, one virtual. And if you don't have that connection to the real world, if you don't have that physical manifestation of the twin, then actually your digital twin isn't a twin at all. it's just a simulation. It's either a simulation of something you haven't built yet, or it's a simulation entirely theoretically and abstractly of something you're not actually connected to in the real world. And those simulations are useful. Those simulations are valuable. They absolutely serve a purpose, but it's unhelpful to call them a digital twin. So we don't. The second key characteristic, and all of these sort of build upon one another, the second key characteristic is this bi-directional exchange of data. A digital twin is informed by what's happening in the real world. So if it's a digital twin of a robotic arm, like the picture here, or a digital twin of a wind farm, like the ones I was talking about earlier, the digital model is updated based upon what's happening in the real world. The robotic arm has just turned through 30 degrees to the left. The digital model must receive that information and know that it has turned through 30 degrees to the left. But equally, the data must flow back the other way. Where the digital twin makes a change, that information must be fed back to the real world as well. And sometimes that's just about keeping the two informed of what's going on. Sometimes it's about control. So the digital model turns through 30 degrees to the left, and that's actually an instruction to the real robot to follow suit and do the same thing. The next piece, and these are all building upon one another. The next piece is this notion of timely updates. There's an assumption sometimes that the physical and the virtual are constantly connected. All of the data is real time. All of the instructions that are passed backwards and forwards are happening instantaneously. And obviously that's nice and useful sometimes, but other times a real-time connection would actually put sort of undue cost and undue complexity into the model. And one very good example of this is in the airline business, where, for example, you might have a digital twin of fuel consumption on an aircraft. You need to know before the physical aircraft takes off how much fuel it's going to need to fly from London to New York. And you use a model to work out how much fuel to load onto the plane. Once the plane is in the air, you don't actually need to be updating the digital twin in real time about fuel consumption. You don't need to know somewhere over Iceland exactly how much fuel has been consumed. But when the plane lands, you absolutely want to offload data about how much fuel actually was consumed. You want to compare that to what the model said. Did the plane consume slightly more than you expected or slightly less than you expected? And you use that to update the model. And you try to understand what happened. Was it windier than the forecast told us, and therefore we were dealing with a headwind? Or was there some problem with one of the engines, perhaps, that meant it was consuming more fuel than it should have? And you use all of this to improve the model, but also sometimes to take remedial action, to go and fix that engine, for example. So in that case, there doesn't need to be a real-time connection between the digital model and the physical plane. The update, it's okay that it happens 9 hours after the plane took off. In other cases, like for example, an autonomous car, the updates absolutely have to happen in real time. If the model is telling you to apply the brakes because the model thinks there's a pedestrian in front of you, the action in the physical car should be instantaneous. If it's not, people are going to get hurt. So timely updates. The update must happen as quickly and as accurately and as reliably as the use case requires. But that requires you to understand the use case. So is it an autonomous car where the model is actually helping drive it? Or is it a fuel loading model for an aircraft where the model is only helping you to optimize the amount of fuel you put onto a plane? Directly related to this is the notion of maintaining state, the fourth key characteristic. And this is important when you don't have real-time constant connectivity. If you are dealing with something, an intermittent connection, both the model and its physical twin need some ability to cache what's happened. They need some ability to cache instructions and some intelligence to only transmit the instructions that matter when the connection is restored. So the robotic arm that we're looking at here, for example, if the digital twin of the robotic arm said, turn left, turn right, turn left, turn right, turn left, all while offline, when the connection comes back on, only turn left should actually be transmitted, because the first 4 movements have been superseded by one another. So that's important too. You don't want to send all those instructions and have a rather manic robot sort of jerking left and right, left and right, left. It should just turn smoothly once left, because that's the final instruction. The 5th key characteristic, the concept of modeling and analytics. These digital twins shouldn't just collect data. These digital twins shouldn't just send instructions. They should be able to model behavior both in the past and in the present, and use that to predict future action as well. For example, back to the wind turbines I was talking about earlier. Analyzing the data about how a particular turbine is operating, when is it going to need serviced? Analyzing that data, which component is likely to be causing the problem? Analyzing that data, which of my set of available field service engineers is the one with the optimal set of skills to send out to fix this problem? And then the final key characteristic is this notion of reporting. A lot of times when we talk about digital twin, a lot of the people hearing the conversation instantly assume this is all about pretty 3D visualizations. You've got a pretty animated 3D view of the robot or the magnetic or the wind turbine or the train or the aircraft or whatever it is moving around on your screen as the real thing moves around in the real world. And there is some use for those visualizations, absolutely, but they're not the only way to get information about a digital twin out into the real world. Just as useful might be a text message to a field service engineer telling them, you need to go and service wind turbine 27, you need to take this part, you need to go to this address, and here's the task you need to fulfill. Simply a text message delivered to their smartphone. That is a useful piece of reporting from a digital twin. Equally, it might be a change on a graph on a dashboard. You might be monitoring fuel consumption across your fleet of aircraft, and you want to see what the flight that just landed, how much fuel it consumed. So you simply have a bar, appears on a graph, and that tells you everything you need to know. You don't need a pretty 3D model of the engine, or a pretty 3D model of the aircraft, or a pretty 3D spinning globe that shows the plane moving from London to New York. All of that's pretty, but completely irrelevant. Equally, reporting might be an API call. It might be a piece of data transferred from one application to another without any visualization at all. So those are the 6 key characteristics of a digital twin. And at Forrester, we increasingly argue if you don't demonstrate all of these, you're not a digital twin. The one other piece I wanted to touch on, and we've sort of alluded to it through those previous examples, is the importance of the past, the present, and the future. And all of these play a role in your digital twin. And we talk about them slightly differently to make it clear which one of them we're talking about at any given time. So increasingly within the research I'm doing at Forrester, if I'm talking about a digital twin consuming data from the past, previous behavior of a jet engine or a robot or a wind turbine or whatever it is, if it's only looking at historical data, you might talk about that as a digital shadow. A shadow looking back into the past. If it's simply understanding what is happening right now, you might talk about it as a digital mirror, reflecting what's happening in the real world right now. So that remote wind farm again. I'm sitting in the control room in Glasgow. The wind farm is off the west coast of Scotland somewhere. I can't see the real thing, but I'm getting a reflection of what it's doing right now. And then the digital twin is the three of those combined: past, present, and future. And pulling data from all of those together to understand what has happened, to observe what is happening, perhaps to control what is happening, but also to make predictions and next best action recommendations for what's going to happen in future. One other piece, and then I want to move on to a slightly different part of the conversation, but one other piece, as we look at the digital twin landscape at the moment, a lot of the digital twins we see out in the wild are produced by individual vendors. So you have the vendor who made your wind turbine, or the vendor who made your robot, or the vendor who made your pump. They give you a digital twin for just that asset. That's useful to a degree, but really doesn't help to solve the broader customer problem. So if you are, for example, a customer operating an entire wind farm of 200 wind turbines, they all come from different vendors potentially, and you don't want those different digital twins from different vendors all having to be dealt with separately. You can see the same thing on this slide here, where you have one vendor has delivered a piece of equipment into your factory and a digital twin for it. Another vendor has delivered a different physical asset and its own digital twin, and a third vendor has done the same. If you're the customer operating that factory, you absolutely do not want three separate independent digital twins. You do not want to look at them on three separate screens on three separate computers sitting next to one another in your control room. You want to understand the entire process, the entire operation, the entire workflow that you care about, and you want to be able to pull data from those different twins to inform that. We're not quite there yet a lot of the time. So there's some very interesting work underway to try and harmonize these digital twins and to create what we often refer to as complex or composite digital twins that pull the necessary information from the underlying models, but then give you an insight into what's really going on across the entire process. There's a lot of work still to do there. So if you're in the market for some digital twins and you're dealing with the vendors of your physical assets, ask them these hard questions. If you, vendor A, how am I going to integrate your digital twin with information coming from vendor B and their digital twin? And don't take obfuscation for an answer. Keep pushing here. It's really important. So one more area I want to look at before we hear from Manju and some of the experiences at Pluto7 is another piece of work I've been doing at Forrester to look at three broad use cases for digital twin. Three different points in the life cycle of an asset where digital twin delivers value. And they do all join together and they all build upon everything I've already said. But depending upon which of the use cases is most relevant to you, it requires you to think about digital twin and the data you gather a little bit differently. So firstly, we talk about a design twin, the particular use of a digital twin in the design and construction of a new product. And here, you're going to be pulling a lot of data from things like CAD. You're going to be pulling a lot of data from things like PLM. You're going to be pulling a lot of data from your supply chain systems as you try to work out how to build a physical product. And here, you're combining simulation of how a future asset might perform in the real world with data coming from prototypes that you're deploying out into the field. And the obvious example of this, there are others, but the one obvious example of this is the automotive sector, where we're seeing digital twins being used to reduce the number of physical prototypes that have to be built. Now, no automaker I've spoken to is saying they will no longer make physical prototypes. They still do, and they still have a value. But by incorporating digital simulations and modeling and prediction, they're able to reduce the number of physical prototypes they build. So perhaps you build 3 or 4 physical models of your new car before it goes into production, instead of building 10 or 20 models of your car as it goes through those different design phases. And so here, you simulate in a digital wind tunnel what you think the aerodynamics will be like. And you get a really good idea of how to optimize it. And you change the shape of the wing mirrors just a little bit in the computer to optimize those aerodynamics. But then you always want to build a physical representation of the car and put it in a real wind tunnel and check that the model was right. And then you want to build a physical model of the car and drive it around a real road on real conditions to see if it actually performs the way your models and your wind tunnels and your knowledge and experience says it should perform. So you're combining the two. And so here, the digital twin is reducing the number of times you have to work in the physical world, but not eliminating them altogether. The second phase where a digital twin can be useful is what we call a process twin, where you're using the digital twin to understand how real world assets, real world systems, real world factories actually operate. And one example of this is Unilever. And they've been working with a number of vendors in this space to build digital twins of their manufacturing processes. And they started off with 1 or 2 factories, and now they're looking to deploy digital twins across 300 of their factories around the world. And those digital twins improve visibility into operations within a single plant, and that's useful. That's making those individual plants more efficient, more responsive, and better able to respond to customer demand. But for head office, the other value they're seeing is by beginning to aggregate data from those 300 digital twins of 300 plants to start to understand how Unilever's business as a whole is actually operating. How are we doing on a particular product line that's perhaps being made in 2 or 3 factories in different places around the world? Are there lessons we can learn from the factory in Brazil that we could deploy to a factory in Europe that's making the same product but is not achieving the same efficiency goals? So what can we learn and compare from those different plants? And we see lots of examples of this beginning to play out across a range of sectors. The third area where digital twin gets interesting, and the one actually where I spend most of my research time, is the notion of a service twin, where we start to use the digital twin to understand how products and services we have built operate once we give them to someone else, once we've delivered them to a customer. And here we're seeing the service twin begin to drive completely new business models, completely new ways of thinking about how different stakeholders around a product relate to one another, and completely new conversations about what data from those assets is worth, and also who owns it and who has the right to make use of that data. And one example of this is some of the work that Airbus, the aircraft manufacturer, is doing with their new Skywise platform. And so within Skywise, which is being operated by Airbus, at the moment, there are about 6,000 aircraft contributing data to the platform. And those 6,000 aircraft are spread across 80 different airlines. Now, some of those airlines are partners, and so they work closely together. And so they're reasonably comfortable sharing data with one another. Others of those airlines are direct competitors with one another. And for them, there's much less willingness to open up and share lots of data with direct competitors. And so one of the really interesting things here is around how Airbus and its partners are thinking through what that data sharing looks like. Some of the data maybe only goes to Airbus and the airline that contributed it. Some of the data will be shared just with partners. Some of the data might go out to OEMs who are making parts. So, data from 80 airlines about how the seats wear may be shared with the seat maker. Data from 80 airlines about how the toilet doors wear may be shared with the toilet door manufacturer. And it was really interesting, actually, when this particular engagement reached the UK press. You can imagine the reaction. Airbus and its airlines are spying on you when you go to the toilet, the headlines screamed. It wasn't actually true at all. Nobody could see when an individual went to the toilet. what they were doing was measuring the number of times the toilet door was opened. They were measuring the number of times the toilet flushed. They were measuring, whether or not there were particular problems that tended to crop up there. Little things like, the toilets at the front of the plane are used more often than the toilets at the back of the plane. Understanding that from the sensor data, perhaps you need to improve the signage to encourage people to go to the toilets at the back of the plane more. Or perhaps you need to take out the toilets at the back because nobody uses them. So you can free that space up and use it for more seats. Understanding how the plane is actually used and understanding how different partners in the ecosystem can benefit from and use that data is where this gets really useful and really important. And then the final piece is the notion, wrapped all the way around, the arrows pointing all the way around this diagram. In theory, at least, the digital twin at design, the digital twin at operation, and the digital twin at the service stage should all inform one another. So information from the use of an asset in the field should inform the design of the next generation. The toilet door handle on an Airbus A380 consistently breaks off. Feed that back to make a better door handle for the next generation of the plane, and much more complex things as well. The turbine blades on a particular class of engine tend to wear out much faster than we thought when the plane is flying in desert conditions, because the sand abrades the turbine blade. So where the plane is going to be flown in those conditions, perhaps use a different engine maker, or perhaps use a different class of engine, or perhaps service the engine more often if it's flying in those conditions. All of this information becomes very important, and these different phases all inform one another. And broadly, that's what I wanted to share with you. Some definitions of digital twin as we see it at Forrester, some use cases for digital twin that we've observed in the market, and some of the ways that you can start to think about how digital twin might help your business, so that you can engage with stakeholders, partners, and providers of solutions to get them to give you the pieces you need to allow your business to make best use of this technology. And with that, I'm going to hand over to Manju to talk a little bit about Pluto7 and what they're seeing in this space. Manju, over to you.
Thank you, Paul. That was a very insightful narration and articulation of what a digital twin is. We at Pluto7, as a founder CEO of Pluto7, I have been involved with about 300 plus customer conversations engaged with Google and enterprises around the world. The terms such as IoT, digital twin, machine learning, AI, smart analytics, data-driven, many terms get used to solve a problem or a set of problems. But again, bringing all of them together is absolutely critical, not just the technology part, but the people, the process, the KPIs, the goals, and the vision. We at Pluto7 enable smart analytics, supporting the digital twin capability that customers look for as they innovate and transform. The digital backbone of smart analytics relies on many aspects. It all needs to start from our perspective, from knowing where you are in the journey, where you are in the maturity curve. Mostly we have seen customers are at the early to middle stage and very few at the advanced stage, and I'll explain what that is. If you start off with the objectives of why you're enabling a digital twin and what are the dependencies, the objectives of why you want to enable a digital twin could be on the right side as it's reflected here. It could be you're trying to improve quality or productivity or efficiency in your manufacturing floor, or you're trying to get better ROI out of your machineries or the equipments, or you're trying to enable a competitive advantage for your company, like Paul mentioned, newer business models that's unique to you. On the left side, to achieve the outcome on the right side, you need to put the foundation thinking what your digital foundation looks like, and you might already be on the journey, and then determine what automations you want to put in place, how are you going to connect your plants and the supply chain. Supporting this are the concepts that we just discussed. Connecting your data. Data is a reflection of your physical assets, physical process, or people activities. Connect the data through the digital thread. Enable the digital twin to be able to effectively help you make a decision or monitor or anything else you want to achieve. Then you've transformed into becoming a digital business or a data driven business. All of this while you're empowering a workforce. As we work through customers, it's become evident that the technology is already there. It's a matter of which vertical you're looking at. There are verticals which have been using it for many years or maybe even decades in some cases. And there are industries who are looking ahead. And we will quote some of those examples as I go through this. When it comes to technology, whether we are looking at what Paul mentioned, IoT is one portion of it. Then you need to bring the data. You need to know the state of the machine through the data. Depending on the volume, the industry uses the term big data. Then you have sensors. Then you have interaction with the digital twins through your IoT devices. It could be even as simple as a smartphone getting a text message. And then you're trying to connect all, centralize this data to you do your simulation and modeling. That could be your cloud computing with machine learning and AI. At the end of the day, these are all technology components to enable, depending on what your process or your business needs, whether you need a real-time update or you want to simulate the state of the machine now and what will happen in the future. These capabilities are available for you. Now, it's a matter of understanding how these capabilities work in harmony with your business process, and most importantly, driving change. Change management is the harder part in this equation. For any digital twin to work, it's always going to work in harmony or tandem with data. And the data, from what we have seen, it's typically a hybrid cloud environment. You have data in your on-premise, you have data in multiple clouds. We enable data centralization primarily on Google Cloud. And when we do that, we understand your business through a business architecture, understand what you're trying to achieve. And as I walk you through some of the examples, we'll talk about how we do that. So smart analytics, which is a combination of getting your data, managing your data, connecting your data, putting machine learning models, not just enabling those models, but operationalizing at scale so that now the predictions that you're doing are automated and it works in harmony with your day-to-day job or task your operators are doing, or your machine or equipment operators are doing on a day-to-day basis. The technology and the digital twin needs to coexist without appearing as a huge learning curve or a threat to the job that's already being done. To do this right, it's important to think about the value first. Why are you doing it? Why are you enabling a digital twin? What are your goals? Are you trying to reduce cost? Are you trying to drive better safety? With COVID-19, there are new scenarios that have occurred which we never thought about, maintaining 6 feet distance between human beings. Risk mitigation. We deal with various kinds of risk, whether it's weather, security, wildfire. Then the overall strategic reasons why you're doing this. How is your industry changing? And when you do this, you cannot ignore the fundamentals. And like Paul mentioned, you cannot just anchor to a set of technologies. You need to go back to your drawing board, understand the ROI of what you already have, whether it's a technology or business process or people assets and your machineries, and what are you trying to accomplish. And with better data insights, not just insights, but also knowing the state of your machines, knowing the history of your machines, what can you do with the data? How do you co-innovate, learning from your industry peers or across industry? I'll walk you through 2 real-world examples on how a digital twin has been enabled. When we talk about digital twin, completely in alignment with how Paul described the 6 key aspects that you need to think about: centralizing the data, connecting the data, and practically it's a multi-cloud environment. In this case, an energy company looked at how can they look at their 200K plus assets distributed across forests, across cities, across industries. How do they monitor those assets? It's labor intensive. There are risks with weather, fire, many aspects. And those devices are not necessarily connected. Some are connected, some are not. How do you connect them together? And some are legacy environment, not just their internal systems, but also the connection devices. Some don't connect to internet, some do. When we looked at the landscape the way it is, the business process the way it is, and the people how they operated, we looked at how you can do proactive detection, how this enabling the digital twins, you can detect risks, threats, or asset going down much early on. That helps the operator or the inspector to look for the failures early on. All of this using the connected data. Data is the representation of the state of how the world is progressing. And when you connect these four aspects of digital threads, digital twin, tracking your assets, and even going to the extent of connecting your ordering system to manufacturing, when there is a failure, how orders get impacted, now you have a much more coordinated business that's running together. For a digital twin to work, just for simplicity, well, I use this analogy many times. Like if you have a Google Home or a smart device at home, you ask a question, you get an answer. Uh, And you're kind of working together and it's getting trained and giving you better answer over time. There is a lot of machine learning and data mining, data searching behind the Google Home that's out there. Now, if you think about the same concept applied for your business, you need you have a lot of data coming in. Like on the bottom left, you have the streaming data, whether it's machine sensors, IoTs, and you have your business data, which is in your ERP systems, SAP, Oracle, coming from your vendors, partners, images, videos. You need to collect all of those. And the architecture cannot be complicated because the data volumes, as they're growing in this case, they're growing from 1 petabyte to 100 petabyte over the 10-year horizon. So collecting the data, processing the data, storing, analyzing, understanding, or applying the data patterns to find insights or machine learning output or AI, all of this becomes part of a foundation that you need for your digital twin to work effectively. And under the hood, when we enable this using Google Platform, the architecture is much simpler than what most people imagine. Whether the foundation that Google runs for running their own search engine, YouTube, it's the same foundation built for the largest volume of data possible on Earth. And when you take an enterprise data and fit into the same architecture, collecting the information, some of them, what Paul mentioned, whether you have wind turbine, what's the state of the turbine, what was the history of the turbine, or your machinery or equipment, what's the future, predictable future. A lot of that prediction of the future happens in your machine learning area. But to have your machine learning work first, you need to centralize the data, connect the data. And to connect the data, you first need to gather the data, whether it's coming through machines, equipments, or human-generated data or legacy environment. And once you create the insight, whether you put it on a dashboard or a text message or a write back into some existing systems or even enable through a chatbot or smart device, that's left to the enterprise solution architect's imagination. In this case, what we had to build had to be thought through for not for the next few years, but next 10 to 20 years. These AI detections help reduce your human labor dependencies, improves the risk detection and compliance adherence. Moving on to the next case study, AB InBev, largest brewery in the world, make about 360 beer brands, Budweiser, Corona, Stella Artois, and many more. When they looked at leveraging these technologies, they looked at many aspects and asked us a question, what can we solve with these technologies in 2017? We picked preventive maintenance. And the background to that is when you think about when we walk through the manufacturing floor and observed how business is conducted, how manufacturing equipments are operated, where human labor is playing a role, and What's the accuracy of the decisions, whether it's manually made or through looking at a BI report or through experience, they arrive at a certain accuracy. When we looked at those accuracies, those decisions had about 70% accuracy or 80%, and they hit a wall. And when you double click that, you notice that it's biases, assumptions, and mistakes that lead to lower accuracy. Then at the end of the day, if you translate all of these, it really translates into numbers, math, and mathematical equation. And that's what got represented into a machine learning model. We looked at many problems and we picked a one where there was ROI is obvious, a downtime. Everybody understands the labor, the supply chain disruption, and the impact of a machine downtime. Can we predict when a beer filter needs to be replaced? Can we predict hours or days in advance? And the answer is yes, we could predict using machine learning model, using the state of the machine now and the history of the machine. And the model then showed a saving of $10 million with a 60% improvement in the yield of beer. Now, when you look at that, you don't just stop at solving that one problem. You look at all the other related problems that you can solve. What about a step before when the beer is being cooked or during the mashing and kilning? How about you go about regulating the knobs to get to the right accuracy? From there on, you have started the innovation journey. When you have to get started with these kind of initiatives or projects, many times technology could be the lever why something gets accelerated, but you have to do it in a structured way, and that's what our services are. We provide business architecture to go back and start from your vision, strategy, approach, understanding state of your business, look at what data foundation, data warehouses, architecture you have, and get you ready for smart analytics and AI. And not only that, make sure that the change management is effective through better collaboration. Having done this hundreds of times, we have built solutions that can accelerate your digital twin adoptions. And the digital twin itself might help you improve your demand forecast accuracy or inventory carrying costs or preventive maintenance or predicting when your shipments will be delayed, because these devices, these digital twins are working to solve a business problem for an outcome at the end of the day. The problems, as you will see it'll continue to be the traditional problem. You want to reduce the inventory carrying cost, you want to improve human safety, or you want to reduce the shipment delays. And if you continue to evolve on using your data from traditional reporting to BI to big data to machine learning and to digital twin, it's a natural progression. You don't throw away what you already have, you build upon it. So in your legacy, whether your data resides in SAP, Oracle, or Sheets, or IoT, new devices that have enabled IoT devices, at the end of the day, you're trying to run your manufacturing plant more efficiently. You're trying to run your supply chain more efficiently. For that, there is a volume. As the data volume goes up, your cost of decision making goes up. You cannot employ more and more labor to just analyze more data and make decisions using more data. You need the digital twins. These solutions act as digital twins to make majority of the decisions, so that you focus on exception-based decisions where you look at 3 recommendations of the items that you need to worry about rather than 3,000 items. Or you look at machines when it could potentially fail through the text message, like how Paul mentioned, rather than monitoring it on a regular basis. Having done this for across industries, verticals, automobile, oil and gas, to high-tech manufacturing companies, what we tend to kind of eventually look at is there's a common pattern of how these adoptions happen. And putting you on a maturity curve is done through a series of workshops, a quick proof of concept, a workshop, 1-day workshop, or 3 to 4 weeks of proof of concepts. Once you understand how the digital twin, smart analytics, data on cloud, and machine learning, all these things really work together and not look at them as different blocks, then the rest of the cycle becomes obvious of taking it into production and transformation. We have seen customers take anywhere from 1 year on an accelerated pace to 3 years. Not because they just want to adopt, but change management takes longer than you think. In other words, if you look at from enabling a digital twin, enabling these capabilities, if you do it right with the right experience, with the support of Google Cloud Foundation that you get with experience that we bring and taking the learnings from know-how like Forrester. It's simpler than you think. It's easier and faster than you think. We have done this many times, and with COVID-19, if there's one thing that has taught us all is to reinvent, reinnovate, rethink about our KPIs. The machines, equipments, technology, ML, AI has been more ready, but at the same time, you have to fit it right and not be ahead of yourself. Make sure your rest of the process and business systems are ready, and more importantly, your people are ready. So there's a method to this madness. Let's talk further in a complimentary workshop that Pluto7 and Google can host to help you out with this.
And Pluto7 for tying so much together about leveraging digital twins in the manufacturing space. A few questions based on the content we heard from you today. First question for Forrester. Every organization has a different maturity curve. How can manufacturing leaders define their position in the maturity curve?
Oh, that's quite a difficult question, actually. First thing I would say is Manju talked about maturity curves very well in his part of the presentation, so refer back to what he said. The next way I would think about this is to focus on the business problem, the business challenge you're actually trying to address. If anyone, I'm sure, Manju, you would probably agree with this. If anyone comes to you and says, hi, I'm a great big company, I'm AB InBev or whoever it is, build me a digital twin, full stop. Your immediate response is, why? What problem are you trying to solve? Where are you right now on the journey? There's a whole host of things you want to know. Just like every other technology, building a digital twin for digital twin's sake is completely the wrong way to approach this. Totally the wrong way to approach this. Please, everyone listening, don't do it. Think about the business problem you're facing. I talked about monitoring a remote wind turbine on the side of a mountain, understanding what a plane is doing in flight, understanding what a train is doing, understanding a Unilever factory, whatever it may be. Understand what the business problem is you're trying to fix. I want to increase uptime. I want to decrease the number of spare parts I hold. I want to make more efficient use of a limited field service resource, whatever it may be. That's the problem you're trying to fix. Then you try and think about how various technologies can be brought to bear to help fix that. Digital twin is one of those. There are others that come into the mix as well, things like IoT that I talked about too. But you're driven by the business problem you're trying to fix, and you align technologies around meeting that goal rather than the other way around. Once you've done that, you also need to think about how the organization is prepared and positioned to actually deliver on the grand idea you've had. Are IT and OT, information technology and operational technology, are those stakeholders and decision makers aligned? Do they even know one another? Do they talk to one another? Do they share strategies and operational approaches to actually solve some of these business problems? Those are the pieces you need to put in place to then start solving the business problem. Please, please, please do not approach this technology first. You will fail and you will spend lots of money and you will be disappointed.
Thank you, Paul. That was a great answer. The next question is for Manju at Pluto7. What are the early successes you've experienced when helping customers implement powerful technologies such as AI and smart analytics?
Well, there are a lot of examples. Now, when we talk in the market about these technologies independently, there's a lot of excitement and imaginations of what AI and smart analytics and these IoTs can do. However, when it comes to solving real problems, like solving for a motorcycle, world's largest motorcycle company, it comes down to identifying parts. When they have 25,000 parts and when labor has to detect the parts and put it in the appropriate bins, they make mistakes. But you apply a digital twin like a set of cameras, taking images and applying classification models, connecting all the historical data from the legacy and new environment, Now you enabled a labor saving of 40-50%, as well as improve the accuracy. Similarly, when you build a connected cars for one of the largest car manufacturers in the top 10 car manufacturers in the world, when they look at connected cars, when your brake is going to fail, and monitoring the progress of the utilization of the brakes itself during your driving patterns and recommending changes is mechanical parts working with data collection and machine learning in harmony, talking to you in speech and text. Similarly, when we work with oil and gas refinery companies, where we had to determine when the drill bits are going to fail, or a company like Cisco, who needed recommendations on how their machines and networking gears are functioning within their customers' environment, and what kind of response are they providing, and how to provide and serve customers better. Digital twin gets embedded in your marketing, sales, supply chain in many different ways than what people imagine a digital twin to be. If I have to simplify that, the customers who really understood digital twin to be a decision making aid, which can actively scan a lot of data and do it better than them, and following the method that Paul just mentioned, we see successes in those customers.
Thank you, Manju. I think that's all we have time for today. Great thoughts on digital twins from both Forrester and Pluto7. With that, we're at the end of today's Google Cloud Partner Analyst Series and the presentation, Putting Manufacturing to Work in Digital Twins. Thank you, Paul and Manju, for the insights you shared. That concludes our program. Thanks for watching.